Hello everyone, this is Seokhyun. I'm a PhD student in Industrial and Operations Engineering at the University of Michigan. In this video, I'm going to present a multi-output regression method dealing with a situation where group information for some observations is missing. This presentation is based on our paper to be published in Inference Journal on Data Science with the same title. This work is done with my advisor, Dr. Raed Kontar, and Dr. Zhenke in biostatistics, also at the University of Michigan. Multi-output regression aims to estimate multiple latent functions for observations arising from a known number of outputs. Here an output can be also called a group. Relative to a separate regression for each group, multi-output regression is appealing as it can broaden strengths by exploiting potential between group similarities, and this often results in improved learning and prediction accuracy. In particular, in the case where one group is too sparse to infer its latent function, like the red group in the figure, multi-output regression can borrow knowledge from other correlated groups with dense observations, which is the yellow group in this example. Such multi-output regression is based on an assumption that the group memberships of all observations are known. However, this is not always true for multi-output regression in real-world applications. More specifically, when the group label is sensitive or expensive to obtain, we may have a bunch of observations without group memberships. The figure on the right side shows an example where observations in gray represent observations whose group labels are unknown, while the group label of some other observations are known. We call this problem as a weakly supervised multi-output regression problem. Actually, observations with unknown labels often appear in a situation where group labels are sensitive or expensive to obtain. Consider that you are collecting clinical data from participants where one group is taking a drug or not, and you're willing to build a regression model for each group correlated each other. In this situation, some people may not want to provide their information about whether they are taking a drug or not. As a result, we will have a bunch of observations without labels in this case. One possible method to deal with this situation is just ignoring unlabeled observations and build a multi-output regression model using labeled data only. However, this method may fail pretty easily when the labeled data is too sparse, and also we give up an opportunity to leverage useful knowledge from the unlabeled data. In this study, we propose a multi-output Gaussian process-based approach, which is capable of using both labeled and unlabeled data while accounting for correlation between groups as well. Before going into our proposed model, I would like to introduce multi-output Gaussian processes, MGP, which is a critical building block of our proposed model. MGP regression is a popular method for multi-output regression due to its advantageous properties such as non-parametricity, uncertainty quantification, and elegant theoretical background. An MGP is a natural extension of the GP, which features correlation between observations. The key idea is just to build a large covariance matrix, which includes within group as well as between group observations. In this example, we have three outputs, and the MGP has covariance matrix where each matrix inside indicates covariance or cross-covariance matrix. For instance, K12 indicates a cross-covariance matrix between the group 1 and 2. With this idea, an MGP can characterize correlation between groups, allowing for transferring knowledge between groups, which is a key property useful in multi-output regression. Alright, Now, let's see how we develop an MGP manageable for using unlabeled data as well. Specifically, our modeling is based on hierarchical base. We first consider an MGP where all M groups has the same all observations, including labeled and unlabeled observations. This is called overlapping MGP in the literature. Then, the multinomial random variable Z determines group membership of each observation. For example, if Z and M is equal to 1, it means that the nth observation is belonging to the nth group and vice versa. The random variable Z follows multinomial distribution, and we separate it by labeled and unlabeled. For the labeled, the group membership probability pi L is given. For unlabeled, we need to infer based on the data. In addition, we place Dirichlet prior on the group membership probability for the unlabeled observations. The Dirichlet prior will play an important role in labeling sensitivity, which we will discuss later on. This is a general weakly supervised MGP framework using hierarchical base. However, if we use an MGP with full covariance matrix, it will be computationally expensive to estimate its hyperparameters. To cope with this issue, we can easily choose an alternative MGP within this modeling framework. In this work, we choose a sparse MGP, which can be more computationally efficient. Let's briefly talk about the key idea of sparse MGP. The key idea in sparse MGP is to assume that the latent functions for outputs are depending on a shared latent Gaussian process, and furthermore, the latent functions are independent each other, conditioning on the shared latent process. Here the variable associated with the latent process is denoted as U. Next, we model the shared latent process through a kind of imaginary points called inducing variables, which are sparser than the observations we have. This is where the term sparse is derived from. This GP construction can be represented as these formulations. And if we marginalize out U, we get a multivariate Gaussian distribution with the covariance colored in red. Using the Urbury matrix identity, inverting this matrix is computationally more efficient than inverting the original one. Okay, now we have a hierarchical model for weakly supervised MGP. Typically, Bayesian inference and prediction takes the following steps. First, we find posterior distributions for latent variables given our data. Here the latent variables in our model is F, U, Z, and pi U. Then we can find a predictive distribution for new inputs by demarginalization with the posterior distribution. However, the key challenge here is that finding the posterior distribution is intractable. Therefore, we use an alternative way to infer the posterior distribution. Our approach is based on an approximation method called variational inference. The idea of this approach is to find a surrogate of the posterior distribution called variational distribution, denoted as Q. Maybe the simplest way to construct Q is the mean field approximation, where variables for Q are independent each other. To do this approximation, VI aims to find a surrogate Q as close to the original posterior as possible. This is done through solving an optimization problem which minimizes KL divergence between Q and the posterior. Interestingly, the optimization problem turns out to be equivalent to maximizing a lower bound of likelihood called evidence lower bound elbow. Once we get Q, while approximating the original posterior, we can easily get the predictive distribution using the Q distribution instead of the exact posterior. Such a VI framework has gained popularity in the GP literature over posterior sampling method, thanks to its computational efficiency and better generalization. In our approach, we slightly modified the mean field approach, inspired by an observation that the variables f and u in sparse MGP can be exactly marginalized out, as we have seen before. This allows us to introduce variational distributions only for z and pu. We will denote a new elbow based on this assumption as the improved elbow. The expression of improved elbow is represented as follows. Detailed derivation is omitted, but you can find it from our paper if interested. This new elbow has several advantageous features. First, this is a tighter lower bound than the classical elbow based on the original mean field assumption, since we introduce a variational distribution only for z and pi u. Furthermore, you can easily plug in an alternative MGP other than the sparse MGP into this lower bound by simply substituting the covariance matrix colored in red. The improved elbow also provides an insight on how the Dirichlet prior plays a role in labeling sensitivity. To see this, let's focus on the term V. In V, we have KL divergence terms including the Dirichlet prior colored by red. As we are maximizing the elbow, the smaller KL term is preferred. We can see the trend of this KL in the figure. In the figure, x-axis represents the probability of group membership. As we go to the edge of this axis, the group membership is well assigned. So, if we have a small alpha 0 like 0.1, then the model prefers to assign a certain group to an observation. On the other hand, if we have a large alpha 0 like 5, then the model becomes more careful in assigning group labels. Therefore, we can clearly see the hyperparameter alpha 0 of Dirichlet prior plays an important role in labeling sensitivity. In practice, we can regard alpha 0 as a parameter to be optimized to maximizing the improved elbow as well. Great. So now let's discuss our experiments. We have 2 case studies, and we will compare 5 models including our model, WSMGP. Benchmark models and their properties are presented in the table. OMGP indicates the overlapping mixture of GP. It assumes GPs for the outputs are independent and does not leverage label information. OMGP WS is an extension of OMGP to account for the label information, but still ignores correlation between outputs. SCMGP is sparse convolved MGP, which is a type of sparse MGP. Although this method considers correlation between groups, it ignores unlabeled observations. SCMGP LP is a 2-step approach where it first estimates labels for the unlabeled observation using label propagation algorithm, and then use SCMGP to transfer correlated functions. Therefore, the comparison with OMGP-WS will show the ability of our approach to leverage correlation between outputs. Also, we can see if our model can leverage information from unlabeled data through the comparison with SCMGP. The first case study is about predicting a substance called C-peptide in the blood. The C-peptide is often considered a better biomarker than insulin because the pancreas excretes C-peptide at a more constant rate and stays in the body longer than insulin. Therefore, it is practically important to know how much C-peptide is produced given a certain insulin level. We will build a regression model between insulin and C-peptide for two groups of people based on if one takes insulin or not. We collect the data set from National Health and Nutrition Examination Survey. Here, some people do not report their information on insulin usage. Here is the result. In the left figure, we can see that our model reasonably recovers the latent relationship between insulin and C-peptide for both groups. In particular, our model outperforms SC-MGP, demonstrating that leveraging unlabeled data improves the prediction power rather than ignoring it. Also, our model is better than OMGP-WS, showing that modeling correlation between two groups can help better predict the functions by sharing knowledge between two groups. We also see the trend that our model specifically excels at the group taking insulin. This is because the group has less observations. Thus, an independent modeling for the group will fail pretty easily. Our model can make an accurate prediction even for the sparse group, borrowing strengths from the dense group that does not take insulin. The next case study is predicting testosterone level. The testosterone is a sex hormone that affects the male reproductive system and physical sturdiness. It is known that the testosterone level depends on age or one's level of obesity. So modeling correlations between such attributes and testosterone level is important in many healthcare practice. Recently, some studies also show that smoke can also affect the testosterone level, motivating us to build the separate but correlated regression functions for smoker and non-smoker groups. To do this, we collect data from the same database as the previous case study. In the dataset, observations are grouped into three categories: smokers, occasional smokers, and non-smokers. Furthermore, we find that some people do not disclose their smoke habits. We compare our model and the four benchmark models. We find a similar result from the previous case study, showing the beneficial features of our model that effectively models correlation across groups while leveraging unlabeled data. This is more clearly shown in the graph below. We show the trend of prediction error in the number of unlabeled observations used in our model with a fixed set of labeled observations. The graphs show that the prediction error decreases as more unlabeled data is used, which confirms our model's power to exploit knowledge from unlabeled data. In summary, we propose a framework for weakly supervised multi-output regression. This is based on MGP and hierarchical modeling, inferred through a modified variational inference method proposed. We apply our model to two healthcare case studies and find that our model can leverage unlabeled data as well as transfer knowledge across groups, which results in better prediction power. Thanks for watching this video, and if you have any questions, please feel free to reach out to me via this email. Thank you.